apologize for all the static in the background. I've been really working on it, and I basically just can't figure out how to get rid of it. So I promised a student I would have some of these videos up. So I'm going to go ahead and make some videos today with the static, and then I'll just keep working on it and maybe ask around to people who are better with audio than I am to figure it out. So what I want to talk about right now is horizontal dilation. So what dilation is, it's when when I took pre-calculus, we just called it either stretching or compressing. So in the horizontal dilation, what we're doing is we're multiplying all of the x-coordinates in our function or in our graph by a factor greater than 1. So before we look at a dilated graph, before we look at a dilation of this graph, let's just think about what happens when x equals 3 on this graph. And I didn't pick 3 for any particular reason, just totally arbitrary. 3 squared is 9, plus 1, y equals 10. So we would expect if we graphed this function that the point 3, 10 would be on it. So let's take a look at a graph. So the point 3, 10. And we see that for our graph, x squared plus 1, the point 3, 10 is on it. So now let's look at now what we want to do is let's take our function and let's horizontally dilate it by a factor of 2. And so, like I said before, the way we do that is we're going to multiply all of our x-coordinates, so we're going to multiply all of our inputs by 2. So the only thing that's changed about our function is this 2. We put our x in parentheses and multiply it by 2. So now let's think about what would happen. What would x have to be if we wanted y to still be 10 for this equation? Let's set this equal to 10. Actually, before we solve this, let's go ahead and look at the graph and see what happens. So we notice that our graph actually has been like squished inwards. And so intuitively, maybe people would have felt putting a 2 in here would have made the graph like wider or bigger. So why don't we think about why it's actually skinnier rather than wider? So, and let's go back to this observation here, where we're trying to figure out what would x have to equal if y was 10 for our new equation. So we're just going to solve for x. Subtract 1 from both sides. I'm going to square root each side. And we see that x equals 3/2. So we would expect somewhere on our horizontally dilated graph for the point 3/2, 10 to exist. Let's look back at our graph. And we can see that this point is on our new graph. So why is this interesting? This is interesting because if we observe this number, our 3/2 is half the size of our original x-coordinate, which is interesting because when we scaled it by a scale factor, when we horizontally dilated our graph by 2, 2 is the reciprocal of 1/2, which is what you have to multiply this to get this. So it seems like we kind of might have discovered a rule here for what happens to graphs when we horizontally dilate them. And that rule is we take whatever x-coordinates we have on our graph and we multiply it by the reciprocal of our factor, and we get our new x-coordinate. And if you think about it, it makes a lot of sense. So we had to plug in 3 for x to get y to equal 10. So the only thing that's changed about this equation is that we're now multiplying x by 2. So we want y to equal 10. We would expect our x to have to be half as big as it was before to get 10 again. And we can see that this works for basically any number greater than 1. So even if we just did 3, and we still want it to equal 10. As you can see, so our 1 is 1/3 the size of our original value, our 3. So we would expect 1/10 to be a point. And so we notice that this is 1/3 the size of this, and then 1/3 is the reciprocal of our scale factor. So let's think about how to apply this rule to something that's not necessarily an equation. So when I was helping out one of my students with homework, they basically had a quiz problem that looks something on the order of this, where they weren't given an equation, but they were given a function. Looks something like this. Make it a little bit neater. There we go. It looks something like that. And so let's kind of pick out some key points on this graph. So we have 0, 0, 1, 1, 2, 2, 3, 0, and 4, 1. So let's say we wanted to horizontally dilate this graph by 2. So what we would do is, like we saw up here, we're going to leave our y-coordinate the same. And what we're going to do, since we want to horizontally dilate this graph by 2, is we're going to take the reciprocal of 2, which is 1/2, and we're going to multiply our x-coordinate, each of our x-coordinates by that 1/2. So let's go ahead and try that. So first, we're just going to leave all of these y-coordinates alone. Our y-coordinates remain the same when we horizontally dilate. Oops. So 0 times 1/2, so 0. 1 times 1/2, 1/2. 2 times, 2 times 1/2, 2. 1. Wow. 1. 3 times 1/2 equals 3/2. 4 times 1/2 equals 2. So plotting these points, we have our 0, 0, we have our 1/2, 1, we have our 1, kind of move it over a little bit, 1/2, 1, our 1, 2, 3/2, 0, and our 4, 1. And we kind of see that our graph is basically the same shape, it's just squished in, and it matches kind of what we saw in these graphs here, where the larger the number we horizontally dilated from, the thinner it got. And if we wanted to graph our y equals 3x squared plus 1, we notice that it's kind of like compressed towards the y-axis even more. So yeah, I hope this helped with understanding horizontal dilation.